In this video, we will determine the interval and radius of convergence of a couple examples from our packet. So let's get into the first example, for example C. And I've named these examples C because I believe I referenced them later in the packet. But let's say we wanted to know, okay, here we have the power series n factorial times x to the n power. It's always useful if you're having a hard time grasping what this means and what this what's going on with this power series, to look at the expansion, like look at the first few terms to sort of see what does this power series look like in its entirety. And actually, another thing that's kind of important, notice that if we, this power series starts at 0, if we were to plug in 0, we would get 0 factorial x to the 0. And one thing you might wonder is, what is 0 factorial? It might be some value that you've never seen or heard of before. You might think it's 0 because you know how factorial, like 4 factorial means I'm going to start at 4 and multiply all the way down to 1. But if you start with 0, what does that mean? But it's actually important to define that 0 factorial is equal to 1 for a very similar reason to why, say for example, 2 to the 0 is 1, not 0. Because it's a chain of multiplication, it has to have an identity of 1. And I think there's still some debate about this fundamental definition amongst certain mathematicians. But in general, it's agreed upon that 0 factorial is equal to 1. But basically, we would start with 0 factorial times x is 0. That would just be 1 times 1. Then for the 1th term, technically the 2nd term, because we're, again, with power series, we typically start at n equals 0 as opposed to n equal 1, which is fine. It doesn't really matter. But we would get 1 factorial x to the 1. And again, 1 factorial is 1, and then x to the first power is just x. The term for n is equal to 2, we'd have 2 factorial times x squared. Then it would be 3 factorial x cubed, and 3 factorial is 6. And then we would have, 4 factorial, which is 24, x to the 4th. And essentially, the coefficients for this series will grow very, very rapidly because factorial pattern, every consecutive integer that we plug in adds another multiplication by a larger number. And so it gets, the coefficients will get larger very, very rapidly. And so the question is, okay, for which values of x does this converge for? What values can we even plug in? As I was saying in the last video, the ratio test is usually what we want to do. So let's just go ahead and do that. So if you recall, the ratio test always is predicated. We need to examine the limit as n approaches infinity of the next term in the sequence to the original term, or the nth term. So, we have the general term, n plus 1 is the next term. And if we're looking at that ratio, we're going to look at what happens as the sequence trends towards infinity. This particular ratio, if the limit is less than 1, the series will converge, the respective series will converge. If the ratio is greater than 1, it will diverge. So basically, we can examine what this limit tells us and use this to figure out which values of x the series converges for. So let's just get right into it. So, we're going to start with the ratio test, noting that this is purely positive, so the absolute values are not necessary. But we would start with an plus 1, which would just be n plus 1 factorial times x to the n plus 1. And that would be divided by an, which is just n factorial times x to the n. And as we've seen already when we were getting into the ratio test, with factorials and exponentials, we can always cancel these things out. So let me just recap. There's a couple rules that you want to remember this will probably be the last time that I remind you about these. But if you want to cancel out an n and an n plus 1 factorial, remember that those factorials do not cancel each other. That doesn't make any sense. But you could always use the rule that n plus 1 factorial is equal to n plus 1 times n factorial. And all that means is, again, how I would usually write this is the whole n factorial will cancel out with the factorial itself, because n plus 1 factorial, I could imagine prying apart the n. I could imagine prying out one of those factors, n plus 1, and that would leave me with the chain of n factorial from there on out. And similarly, x to the n plus 1, I could always use the rule of algebra, which is that it's equal to x to the n times x to the 1. Or, basically x to the n, this whole x to the n will cancel with just this n, and it will leave me with a x to the first power. And actually, I lied. I'm sorry. I just said that it was strictly positive, so the absolute value does not matter. That is not true because x is something that we don't know. That is one of the key differences with a power series, as it's a series, it's a polynomial, and x definitely could be negative. So we definitely do not want to lose our absolute value here. So my bad. I just disregard that from before. So you don't want to get rid of your absolute values when you're working on the ratio test with power series ever. But a lot of the times with regular series, it's okay because they're strictly positive. But x, there's no rule that says x has to be positive, of course. So anyways, a lot of this drastically simplifies. And what this would leave us with is the limit as n approaches infinity of the absolute value of n plus 1 multiplied by x to the first power, which is x. And now also n plus 1 is strictly positive, but x is not. So the absolute value, I could move it around just the x itself because, again, the absolute values have sort of a distributive property where we could split them term by term, but basically the absolute value of x will make sure this is positive. Now also, since this limit, the limit within the ratio test is only concerned about the pattern as n approaches infinity, the x is a variable that's part of our power series itself. This can be passed through the limit, and that's how we can solve the limit, because obviously we don't know x, so we won't know what happens as n approaches infinity. But what we could see is this, that we'd have the absolute value of x times the limit as n approaches infinity of n plus 1. And of course, this would be equal to infinity, assuming x is not 0. If x were 0, however, and thinking about the power series itself, this is kind of a dumb component of the power series. If x were 0, well, we'd have 1 plus 0 plus 0 plus 0 plus 0 plus 0. It's like in a polynomial, right? If you plug in 0, the whole thing is 0, even if it's an infinite polynomial, except for that constant term. So technically, this power series converges if x is 0. However, if x is not 0, this limit is infinity. And so, okay, well, what does this mean? But if you remember, so what we're doing is we're using the ratio test. And the ratio test tells us that the series converges if the limit is less than 1, and it diverges if the limit is greater than 1. Infinity is definitely greater than 1. So what that means, again, by the ratio test, is that this series, I'll go ahead and write it out as this power series. This power series diverges unless x is equal to 0. Because specifically, if x is any other number, this limit is infinity. Infinity is greater than 1. And again, if the limit of the ratio of the terms of the sequence itself is greater than 1, the series diverges by the ratio test. And again, I could reference, what it is we're doing by the ratio test. Now, again, it will converge if x is equal to 0, because this limit would actually be 0. And you might be wondering, okay, well, wouldn't that be 0 times infinity? Isn't that an indeterminate form? But the reason why it's not is because 0 would be plugged in a lot sooner than we're solving the limit. So this would be the limit as n approaches infinity of 0, which is 0, because that's just a constant. So it's not really 0 times infinity, because you would want to try it. You would want to plug it in here. So anyways, but again, at the end of the day, it's really silly for the value of 0 anyways. At the end of the day, this is essentially how I think of it, is this power series is relatively useless because there are no values of x for which it converge except for specifically 0. And you might be wondering, okay, well, why are we looking at this if it's useless? But basically just some practice with the ratio test and the ideas behind determining convergence from there. Let's do another example. So the next example in the packet is the power series 1 over n times x minus 1 to the nth power. So we have a power series centered at positive 1, whose coefficient is 1 over n. And actually, there is a typo in this example, because if you're looking at this, you'll notice this doesn't make any sense, because n cannot be 0 because it has a 1 divided by n as the coefficient. So what I meant is that this power series needs to start at 1, not 0, which is obvious by looking at it. It's just a little typo. But basically, obviously, you need your terms in the series to be defined. And they don't have to start at 0. It is just typical that they do start at 0 for reasons we will see more further. But basically, if we're trying to determine the convergence of this power series, we need to, again, start with the ratio test. So let's get going, because, again, our goal is to figure out when does this power series converge. But if we were to look at the expansion of this, we would have x minus 1 to the first power as the first term times 1 over 1. Then we'd have plus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. And again, it's kind of like we have this particular power series, and we want to know which values of x does this converge for. Which, you know, in our last example, basically nothing. It converged for nothing. And this one's a little bit more difficult. But let's go ahead and basically the ratio test will help us to figure out which values of x this power series will converge for. So starting off with the ratio test, we'd have the limit as n approaches infinity of an plus 1. So that would be 1 over n plus 1 times x minus 1 to the n plus 1. And that would be divided by an itself, which is 1 over n, x minus 1 to the n. And as usual, we have a n plus 1 x. Let me finish my absolute value before I move on. We have n x minus 1s, and we have n plus 1 x minus 1s. Of course, all of these will cancel with the n of those, and we're going to be left with 1 left over. So let's cancel the common factors. All of those will cancel with those n's, and I'm going to be left with x plus 1. Now, another thing, just like in the last case, n plus 1 and n are strictly positive numbers because, again, we're dealing with this series starting at 1, going to infinity, where they're not negative. So the absolute value, if I'm thinking about it, if I apply an absolute value to this, I could just drop it because it is positive. However, with the x minus 1, basically what I'm going to do is write it like this. I have and also, since I have a fraction divided by a fraction, I could flip and multiply. So if I flip and multiply there, what I'm going to get is the limit as n approaches infinity of n over n plus 1, and then it's going to be multiplied by the absolute value of x minus 1. Again, and that will be to the first power. So notice I've moved my absolute values around x minus 1, because again, x could be negative, and so I don't want to ignore the absolute values within my ratio test. They're very important. But with the n plus 1, the n and the n plus 1, I don't need them because those are positive. And, you know, similarly to the last example, x minus 1 has nothing to do with n, though this can be passed through the limit entirely. So this would be equal to the absolute value of x minus 1 multiplied by the limit as n approaches infinity of n over n plus 1. And this limit, since it is a equal polynomials of equal degree, will just be 1. This whole thing. So the limit will trend towards 1. And so what I'm going to be left with is simply the absolute value of x minus 1 as the limit given by this. So if you know, it might become easy to get stuck here and say, okay, what does this mean? What conclusion do I draw from this simplification? But so if you remember, since we're using the ratio test, what it implies is this original series converges if this ratio is less than 1. So essentially what we want to do is, after we simplify our ratio, we set it less than 1, and this is where our series will converge for. So basically this is the interval of convergence, and what I get is an inequality, which the solution to that inequality will be what we call the interval of convergence. But basically now, next thing I want to do is solve for x. And it might have been quite a while since you were in like an intermediate algebra course, or a course where you had to solve such inequalities. But if you have an absolute value within an inequality, the way I like to do it is basically I refer to it as an inequality sandwich. Basically, the solutions will be boxed in between -1 and 1. It's a rule for if you have an inequality, solve for less than 1. So let me just write this, because again, I know intermediate algebra, this is just a little thing. But if you have a structure that looks like this, it is equivalent to is equivalent to negative c less than x less than positive c. Because if the absolute value of a number will be less than something, it means that it's greater than the negative value and less than the positive value. And this is just a rule from intermediate algebra. Anyways, but basically, if I want to solve the inequality, I could use that equivalency to solve for x. And then if I add 1 to both or all three sides of the inequality, what I would get is 0 greater than or equal to x less than or equal to 2. And basically what I get is an inequality which says that when x is between 0 and 2, this series must converge, so by the ratio test. So basically, or if I wrote it like this, 0, 2 in interval notation is the interval of convergence. And so and this is by the ratio test. So if this is true, the series converges absolutely by the ratio test, because that's what we're doing, right? We apply the ratio test, we get an answer to that limit, and if the limit is less than 1, our original series converges absolutely. So what we've solved basically is that if the value of x is between 0 and 2 here, the series will converge absolutely. Also, so if you think about, remember the ratio test has 3 parts. If this is greater than 1, so another thing is if x minus 1 is greater than 1, the series diverges by the ratio test as well. And so what that implies is that if the exact opposite solution, which would be if x, so this would also equate to if x is greater than 2 or if x is less than 0, in either of those cases the series will diverge. But the other thing is there's one other important thing which I like to call the boundary case, for which the ratio test is inconclusive. So if you go back and look at the ratio test, remember there was a third part of the ratio test where if the limit was equal to 1, so there's like a third possibility here, this final limit, which was the solution to our limit, if that was equal to 1, the ratio test actually was inconclusive. So this is one issue with using the ratio test to find the interval and radius of convergence. But basically, in one specific case, we don't actually know. And what that means is, like, we know the series converges between 0 and 2, but what about it at the boundary? So basically, what about at x is equal to 0? If you actually solve this equation, if you remember the process for solving an absolute value equation is you want to drop the absolute value and do a plus or minus. Basically, there's 2 answers to this equation. X minus 1 is equal to 1, or x minus 1 is equal to minus 1. And if we solve this, what we would get is x is equal to 2, or x is equal to 0. But basically, once you've solved the first, there's a commonality here to where you don't have to solve all of these absolute value inequalities and equations every single time, because there's some patterns at the end of the day. But basically, what I would suggest is that when you solve your original interval of convergence, basically I sometimes call them the tails of the inequality. The inside will converge. The outside, meaning everything else, will diverge. However, at exactly the endpoints, at either 0 or 2, it may or may not converge, because at specifically the edges, the boundaries of those inequalities, the ratio test will always be inconclusive at those specific points. And as we see right here, when x is equal to 2 and x is equal to 0, we're not really sure. So your next question might be, well, how do I figure out if basically the ratio test is inconclusive? Let me just write it out. Ratio test inconclusive. Basically, what I would recommend is plug it in and see what happens, because there's specific cases and we have to use a different test of convergence. So let's specifically examine them in those 2 cases. So actually over here, what I'm going to write about is what about the boundary cases, because I'm running out of room on our notes. But let's start with x is equal to 2. If I plug in x equal to 2, what I would do is plug it into the original series representation. If x is equal to 2, what I would have is the sum as n goes from 1 to infinity. I would have of 1 over n. And if I plug in 2 in the in for x, what I have is 2 minus 1 to the n, which is just 1 to the n. And 1 to the n is, of course, just equal to 1 regardless. So basically what I get here is, let me just erase that. This is just the harmonic series. If x is equal to 2, this power series is exactly identical to the harmonic series. Because notice what I get is 1 minus 1/2 plus 1/3. Sorry, I'm plugging in 2. So 1 plus 1/2 plus 1/3 plus 1/4, which is just the harmonic series. So harmonic series, and basically this diverges as we've already solved before. So harmonic series diverges. This is one we've done many times, but this is a divergent series. So basically in this case, the ratio test was inconclusive, but when we're looking at that particular series, what I'd suggest is plug in x equal 2 and then you have to figure it out using a different test. So we could either use the integral test or whatever, but in this case it's a p series, which is well established to be divergent. Now in the other case, let's say that x was equal to 0, because it could be that both the boundary points converge. They could both diverge. It could be one, it could be the other. We don't know. You have to figure it out. You have to plug in x and do the math and examine what series it is at that particular value of x. So essentially, the complexity of a power series is it's an infinite series that could have any pattern. You know, there's a lot. It's like a bunch of different series put together, and each case has its own unique behavior. But if we plug in 0, let's see what happens. Well, what I would have here is n goes from 1 to infinity, again, of 1 over n. And now I would have 0 minus 1 to the n. But this would be minus 1 to the n times 1 over n. But basically, notice that this is the alternating harmonic series instead, because it would start, it's not exactly the same, because it's actually starting at a -1 instead of a +1. But it's almost the same as the alternating harmonic series that we have studied as well in past in our lecture. And as you probably remember, you may remember, the alternating harmonic series converges by the alternating series test as well. So basically what I'm saying here is that our interval of convergence that I wrote before was actually incorrect, because it actually also converges at 0. And our final answer for the interval of convergence would be it converges for all values between 0 and 2, as I solved right here, but it also converges at the left boundary point because, again, the ratio test was inconclusive at the edges. So we need to check those out individually. But it did not converge if x was equal to 2. It'd be a divergent series. And short summary here, solving the interval of convergence of these things can be quite difficult just because there's all of these little facets between it. We need to do the ratio test. We need to solve our inequality. We need to check the boundary points. Again, we'll do another example. This video is getting a bit too long. And last, also the radius of convergence, one other thing. And I'll just write this as r is equal to 1. It's always the distance from the center of the interval to the edge. But another way you can remember the radius of convergence is it's always going to be, if you take the width of the interval and divide by 2, so here 2 minus 0 divided by 2 is 1. You could solve that in a number of ways, but essentially it should be solved from the original inequality. But yeah, in the next video, we'll look at what's called the Bessel Function, a pretty cool example of another power series, and we'll figure out its radius of convergence.